Hello, my name is Caleb Gilcom. We are Group 4. We are the Reflector Dish Imaging System, or the RDIS.
I'm Blaise Ambrikowski, I'm a mechanical engineer.
I'm Devin Doty, I'm a mechanical engineer.
I'm Sergio Califano, I'm an electrical engineer.
And our advisor is Dr. Sabuni. So for the introduction to this project, Toby Hanna Army Depot services a bunch of military equipment, mostly antennas and radars. One of the systems they service is the JTE Joint Threat Emitter System for the Air Force. These dishes will come in with damages such as warping and over-tightening of the arms and dents from debris. And Toby Hanna currently doesn't have a way to actually locate and identify where this damage is on the dish. So they asked us to design a system to find and locate the damages that's on the dish's surface so they can fix it.
As a demonstration, we prepared antenna simulation here. On the left, you'll see an antenna model. This is the CST. And on the right, you'll see the S11 parameters of the antenna. As you can see, around the 18.9 gigahertz range, we achieved minus 47 dB of radiated power. And if we take a look at the dented model, as you can see, a small dent has been introduced into the surface, and the S11 parameters have been radically changed. And you're only able to achieve minus 37 dB, and that's around 21.3 gigahertz. So radical change just from introducing a dent into the surface.
So Toby Hanna wants to be able to identify the size and type of damage on the dish's surface so they can go in and fix it. They want the system to produce a clear and easily readable 3D model so they can find the deformations location on the surface of the dish. They want it to be easily navigable. They also want the system to be portable so they can switch between different dishes. So we designed a 3-part system that will have 2 different mounting plates for the 2 different size feed points on the JTE's 2 8-foot dishes. It will compose of a housing unit that will hold all of our electrical components that will turn in the theta direction, a 3rd part that will hold our measurement sensor, which will turn in the phi direction, and also get the radial distance from there.
So this is our design. This is 2 pictures of our design from Fusion 360. This is how we're planning on meeting the requirements. The configuration on the left, that will be for the smaller diameter feed ring. It has a 5¼ inch feed mount. And then on the right side, we have our second configuration for the larger feed ring. So the lower section, that's our scanner housing. It houses our electronics. On the lower end of it is our actual distance sensor. Here's our mechanical specifications. So the design will be composed of a scanner, which is in the middle. That's a cutaway view of it, showing some of the electronics inside. It holds all of our electrical components, and the scanning unit on the bottom side. And then we have our 2 interchangeable mounting units because, as Caleb said, we have 2 different size springs. The left side's the smaller one, and the right side's the larger. You can see some spring-loaded items in there, and rubber pads will get into that very soon. Now the other part is we're looking at doing production with metal parts and 3D printing. So everything except the top left corner will be 3D printed. We're looking at that because it is a prototype. It's the easiest to manufacture with, and parts are relatively cheap and strong when they are produced. And then the numbered items are 4 housing components. So this is the main housing. We're looking at ease of production, ease of maintenance, and ease of access to the electronics when the time comes.
So, as my associates previously mentioned, we have 2 different mounting units, one for the small size feed ring and one for the large. To help them stay in place in the feed ring, they're designed with taper, so that way they don't fall out to the bottom. We also have spring-loaded pads in both feed ring setups. That way it doesn't turn. The spring-loaded pads have rubberized feet, so that way it doesn't want to paint at the feed ring or turn when it's taking these measurements. Both heads are quick attach. So here we have our 1 motor setup, the one that's rotating this way. Attached to that motor is a little metal plate thingy that's using a grub screw screws into the shaft of the motor, and 2 other screws screw into that plate through that top plate you can see. That's in the mounting units themselves. 4 screws hold it into the mounting unit, and the 2 screws towards the center hold it to the motors so it can turn. And we have easy swapping between the mounting units and the feed. So,
To illustrate how our system works, we prepared a real animation. So on the left, you'll see a bird's eye view of the dish, and on the right, you'll see a side profile of the dish along with our system, which would be that cylinder there. On the top, you see a representation of circuit coordinates. So we'll be getting the R value from a distance sensor that would be mounted onto our system, and the theta and phi values we'll be getting from 2 separate motors. You note based on how many steps the step motor is taking. If we continue the animation, you'll see that our system will scan a line across the dish. Then that top step motor will take a step and it will scan another line. And it will continue doing this until the entire surface has been scanned. So going to the electrical specifications, so that top step motor is going to have a step size of 0.45 degrees and should be able to rotate 180 degrees. And that bottom step motor will have a step size of 0.125 degrees and turn 120 degrees. We're going to be using micro-stepping to achieve these smaller angles. The smaller the angle we can rotate, the more data points we can collect on the dish. The distance sensor should be able to capture distance with a V point in the dish. We have to provide 9 volts to the Arduino and 12 volts to the step motors. The Arduino should be able to transmit data automatically to the laptop, and the system should be able to receive start and stop commands also from the user. There should be an LED indicator circuit, so you know the system status, if it's on standby, active, like what's going on. And when this system is done scanning, there should be a laser pointer to like highlight where the depths are on the dish. Go on to the electrical components. We're using Arduino to control power. Most of our components, we'll be using NEMA 17 step motors because they're cheap and they can be micro-step. And then the 84988 motor driver will be used to actually enable us to micro-step separate step motors.
We're also going to use essentially a laptop charger to get the 12 volts we need for our system from the 120 volts AC. We're going to use the VL53 LOX time of flight sensor to get our measurement distance data points, and we also have a laser pointer on board so we can point out where on the dish the defects are. For our computer specifications, the program must be able to control the stepper motors so we can get the ankle data. The system must be autonomous so that once the techs start the actual system going, they can leave it go and do work on something else. It must take distance measurements from the time of flight sensor, the angle measurements from the stepper motors, can take them and set them to Excel where they're going to be stored on a table as spherical coordinates. That table of spherical coordinates will then be converted to Cartesian coordinates. Those Cartesian coordinates will be used to graph a 3D image of the map of the dish surface in Excel. We also want the system to display the system status on the screen of the laptop, whether that be ready to go, mapping, or there's an error. This is our real world budget. As you can see, most of our costs in this budget is coming from labor. We decided to use GS9 on the government pay scale for our pay rate. That is for 4 engineers working about 4 hours a week for 2 semesters. For the time span of 2 semesters, this also includes custom machine parts that we need for our design, and that's where most of our $11,000 total is coming from.
For comparison, here's our actual budget, what we're actually spending on this. Our biggest costs through this are our motors, the drivers, and the filament that we're using to 3D print this house. Other than that, as you can see, it's about $257.11, which is just a hair over half our budget. This is good for us because it allows us to have padding in case we break a lot of components and need to change them, or if we screw something up royally and need to order a lot of different things. So we have a lot of wiggle room as an attorney.
So here's our WBS breakdown structure. Broken up into 4 parts: mechanical, electrical, computer, and testing. So for mechanical, we have our feed point mount and the scanning body. For electrical, it's broken up into where the components are located. So we have our external components, the feed point components, which is the top step motor, the scanner body components, which is just the Arduino and the drivers, along with that bottom step motor and the LEDs, and then the scanner head, which will have the TOF sensor and the laser pointer. Going to the computer, we have our Arduino commands, so that it can actually communicate with various components. The Excel Arduino interface, so that's taking those spherical coordinates, converting them to Cartesian. Also the user interface and any error handling also. And then the actual modeling commands, where we'll be taking those Cartesian coordinates and plotting them in a 3D graph. And then finally, we have our testing, which is just ensuring the dimensions are correct, testing the components and making sure the step motors and LEDs are all functioning properly. And then obviously testing any Arduino functions and Excel functions that we write.
entire project. The red dot right there, that's actually today, our presentation. The second half of the year, I'll get into in the next slide. So this is our testing plan coming into the spring. From now into January, we're hoping to obtain all of our parts. Then from there into March, we're planning on testing. So what we're going to be looking at is testing the individual components. So like our Arduino, actually coding it, testing it, making sure they work, stepper motors, seeing if everything goes together in a nice symphony. And when we get to the point, we're going to go up to Tobyhanna and actually test it out on the dish and see if it does what we're hoping to do. Now, our first test phase is of the initial prototype. As I said, it's going to be between January when we come back and in March. Now, we're going to have a 2-week period where we're going to go and evaluate its performance and come up with design changes to it, and if possible, or if we have to, a prototype revision where it's almost a new reconstruction. And then our final testing will be some point between March and April, right before our second presentation.
So our plan for spring of 2025, some of our major milestones will be getting our off-the-shelf components that we plan on ordering before we leave, so we have them right away when we get back next semester. We'll finalize the initial prototyping design. We will do our testing, and then we will finally prepare our results for the presentation in the spring.
So for the code of ethics we looked at NSPE. And as of right now, unless something drastically changes with our project, we are slated to greenlight and follow both these codes of ethics you see on the board. So it should be good. And for our standards, firstly, we follow OSHA standards that they've been utilized for 51 pounds. We're slated to have around 10 pounds at most as it sits right now, so we're well under that. Lasers must be 60825-1 compliant, which basically is just they must control radiation emitted by the laser itself. The project will cost less than $500, as previously stated on the budget slides. It's around half that right now, and it will be completed in 2 semesters. So next semester, we should have the prototype set.
So we would like to acknowledge some people, Mr. Chester Trejewski, sorry if I said your name wrong. He helped us coordinate this effort between Tobyhanna and Wilkes. And then Mr. James Jarrett and Ricky Saunders, James is back there, and so is Chester. They gave us this idea, which was really nice of them. So very thankful for that. Wilkes faculty, Dr. Sabuni, for being a good advisor and coming up with the idea of simulating a damaged antenna and a normal antenna to see like how damage can actually affect the performance. And thank you to Dr. Bednarz for providing helpful feedback during project presentations. And I'd also actually like to thank Dr. Bedore because she came to Tobyhanna one day and we showed her our project and she liked it. So thank you, Dr. Bedore.
Here's the references. These are just for the modeling purposes. In Fusion 360, we use the hardware from the capacitor card, the stepper motor, CAD modules, and the Arduino. And then the antenna simulation guide. They use, I don't know, one program to actually come up with our simulation, but whatever wizardry they work with, they can use a video to at least get a little help with it. But that's the link there.
Any questions, comments, concerns?
Thank you. You mentioned a 0.45 degrees scan resolution that you needed, but did you start with a resolution on the dish itself? What the size of the feature was you needed to be able to examine?
So the deformations can be all kinds of different sizes, whether it be like a small, like ping pong ball size dent or something even smaller than that. So we really don't know what kind of size dents we're going to see coming in from the field. Could be a rock got thrown at it because they were bored, I don't know.
So how do you know that 0.45 degrees is fine enough?
We're not sure. We have a slide where we went through and calculated all the different data points. The one at the very bottom is currently what we're working with. It's the point 1/4 and 1/16, and that gives us about 420,000 data points. So we think that should be enough, but we can go up and down a little bit each direction. So if we need to increase it more or less, we can find out.
We won't know.
One other thing, you mentioned time of flight, but you never said time of flight of what?
The sensor
is it a laser or
Yeah.
using sound or what?
Yeah, it's a laser. have a place that's
Would it really help if at the beginning of your presentation, you sort of given us the big picture?
Okay.
You sort of showed a picture of the antenna, and then you jumped into a housing without any reference to how it's mounted, any idea of what it's actually doing, what the coordinate system is for doing things. And, I mean, I figured it all out, I think, but you need a little bit better organization at the front end. Looks very interesting. Thank you.
Following on that, the very first slide about the frequency versus. I think you should do a better job of getting your audience. Very clearly looking at the slide, and for someone who's looking at the antennas and really, spend maybe 1 minute. You find the diagram, you set the column, we're going to click the diagram, what that is, what it should look like. I mean, you lost it. Like the mechanical, that's not the touch on the sound of the products. So, we're organizing to educate the audience. You are not presenting your job now. For now, I think it's more than enough because they know the problem is. For us, you should probably kind of walk us through the problem first.
Could you go back to your bullet point? So what the bullet point I can see? So could you tell me like why you were looking at the magnitude, right? Like it went from 45 dB to 30 something dB, right? But could you explain to me why the frequency also shifted?
So that's one parameters are basically, and Dr. Sweeney, correct me if I'm wrong, a measure of how well an antenna can read power. So when you're at 0, so if this graph was, let's say 0 dB, if you're at 0 dB, it's not radiating any power, it's basically a useless piece of metal at that frequency. So the more dB you get.
Okay, so my question is, do you care about the magnitude or you care about the frequency?
Both. So
You are extracting both, or is that what you're doing?
right. So if you look at the characteristics, so if you look at the graph at 18.9-ish gigahertz there, you see that big dip. So the antenna operates best at 18.9 gigahertz. That is where it's radiating the most power. Whereas if you look at the top of the graph, like 18.5-ish gigahertz there, you're only radiating about a little over 15 dB. So it's not very effective at that frequency. If we go to the dented antenna, you'll see that the frequencies at which it operates best have completely shifted. So whereas the other antenna was really good at 18.9 gigahertz, it's no longer radiating 47 dB at 18.9 gigahertz. It's only hitting 21 dB at that frequency. So the entire profile has been shifted from introducing that small dent there on the surface.
My question is like, from these two comparisons, is the frequency information more crucial to you or the magnitude information more crucial to you?
You need both.
You need both, yeah. So, do you need a frequency analyzer to do this? How do you embed this in your, I guess the computation, this kind of analyzer, is it done online or offline?
This is done, you'd have to hook this up to the full system actually.
And this is a simulation.
Yeah, this
But
is
eventually in your physical system, how, like you collect the data, you really couldn't do that frequency analysis online or in real time, can you?
So Toby has a way of testing these dishes for whether or not they're actually operating where they're supposed to be. And if they're not operating where they're supposed to be, that's when they would introduce our system to try to find the dent on the system itself. So the actual frequency analysis, we're not doing. We're just using this to show how detrimental a dent introduced to the dish can be.
So what we're producing is a 3D map of that surface. We're helping them locate where the damage is.
We're helping them locate where the deformation is rather than tell them, oh, there is deformation.
Oh, okay, so you're giving a kind of mapping.
Yes, so like have you ever seen a pulp-top scanner?
I mean, okay, so if that surface, all you need is go there to your visual inspection, you can see the dent, but what's the point?
You won't always be able to see all of them. Some of the dents are going to be smaller, and also the dish can warp.
You see my point, right? You're basically generating a map for this 3D map for the surface of this, and so you can detect those micro dents.
Yeah.
As well as sync working on the dish, because
I see. I thought you were using the frequency, the signal laser to detect the frequency change, then you can figure out
No,
what that is.
no.
Because
That
that's
laser is for distance.
you're just doing a mapping.
Yes.
So, those radar or those antennas, they're 8 feet in diameter. It's very hard to pick up every single deformation. And even something small enough can throw off our initial bands. Now, we're not testing that part. We're specifically doing a surface map of it.
Do you ever consider just using a LiDAR? That's because they're commercially available.
Yeah, so the issue with using one of those is most of them you have to get really close to the dish, so it's like the actual distance used is like here. And also most of them have their own proprietary software, which have to get cleared through the government systems, and that can take a lot of time.
Driving, you can scan all 100 meters at least. What do you mean?
So when we looked at the 3D modeling, it's like different, like we looked up different 3D modeling systems online that you go through and see them. Some of them are $30,000, like actually like they're all kinds of crazy expensive. And then also anything that would require, like if they wanted to get a 3D image of the dish, so they could actually see it and then map it and then go in and fix it. So they could give like here's what the dish looks like, here's the dead, hand the blueprint to the tech, and be like fix the dish's face. That would require a software to actually map it, and getting a software cleared to the government systems can take a good chunk of time, so it wouldn't be very efficient. And this is where they can use it with systems they already have in place and software they already have in place, and then they can just go straight.
So you're basically creating a customized, a smaller version of LiDAR.
Yeah,
Is that the
Those
interpretation?
are the Excel pages.
yeah, I can show you the actual mapping.
We have a sample.
Okay. I mean, if you said that, I said this, I would understand. Okay. Otherwise, it took me.
We were at a very short time limit to get everything we needed to cover.
Yeah.
There was a lot to cover.
Yes.
We did have an appendix.
So yeah, this is essentially what we're trying to do. This is a very small demo with very few data points, so that's why it looks kind of weird. But this is essentially what we're trying to do. So that's the actual XY coordinates that are calculated using this basic spherical conversion. And then using this formula here, I filled in the rest of the table. The NAs essentially are values that can't be calculated because of the sign, because of the magnitude for the inverse, for the cosine value is either bigger or smaller than 1 or -1, so arc sine can't work. So I gave them Excel NA, which Excel automatically ignores and doesn't graph, and then you get that system, and you get that graphic.
So you're 100% sure with the laser you're using, you can detect whatever the fine, smaller things you are looking for.
Yes.
You're sure about that?
Yes.
Okay, if that's it, then you have no more risk. Very good.
One question, during your presentation, you mentioned that in order to collect the data, you use like polar coordinates, right?
Yes.
But then like, when you generate the image, you are using partition. So what is the reason to work with different coordinates?
So the Cartesian coordinates are easier to plot in Excel. It's just a quick transformation process between the Arduino and the computer. So it's easier when we're using the actual system to plot the polar coordinates because we can get the angle of the motors and then the radial distance from the laser sensor. That can all be transferred into Cartesian coordinates and become a laser plot.
Thank you.